Shabat. Georgy Borisovich Shabat, he's from Moscow. I spoke with him just before the talk, and I repeat what I thought 3 months ago when we had a talk by Bogdan Olenik. In Russia, they speak how many diplomas you need to be intelligent. And the answer is 3. And the question is not in which branches, but who has these diplomas? You, your father, and your grandfather. In our case, Georgy Borisovich, he is a professor, doctor in science. His brother, he also was professor and doctor in science in mathematics. And if you speak about his father, Boris Shabat, I think that the people from my generations, all of them have studied his book on complex analysis, his textbooks on complex analysis. So you are very, very intelligent. And the title is Dessins and moduli spaces of curves. Probably he tell us what this means, Dessins and enfant, but in translation in English, this means children drawing. Okay, please.
Okay, thank you very much for your introduction. I'm happy to give a talk to you. It was the first time in this summer when I visited Bulgaria, and I spent a couple of weeks in a lovely place, Lozinets. Then I got acquainted with Christa Iliyev, and so here I am. So you heard the title of my talk. Now here is the brief plan of what I hope to stick to. Well, we'll move along it. Okay. So first, I try to explain what does the end mean, how I relate the rather special theory of descent d'enfant that I will give an introduction to, and the well-known object of classical algebraic geometry. So as I write here, I omit completely something very abstract, though maybe I should mention what I didn't write here on the slide, that Mochizuki is an outstanding Japanese mathematician, a leader of large school, who pretend that they have proved the ABC conjecture. And in fact, nobody understood their texts completely. It is an open question whether they did or not. However, they are doing very interesting, very abstract mathematics related to the topic of today's talk. As for our, sorry, do you see my, how do you call my pointer, small pointer here as a hand?
Yes, we do see.
Okay, so today we avoided and discuss a very down-to-earth object. I hope they are going to be quite clear. But before we turn to mathematics, I give several historical comments, because this theory is not at all a usual one. And here I try to explain briefly how this theory was born. So there were events in Grothendieck's life that have nothing to do with mathematics and nothing to do with the object of today's talk. When and as a result, Grothendieck left any institutions, including the one he worked for many years, and in math community in general. So he returned to his native university in Montpellier, and then he tried, but he remained a professor, and he tried supervising student. So this is with bagage mathématique modeste ou moins modeste. It is in polite French. It means that his students knew nothing, knew no mathematics at all. That's why he had to choose some elementary topic, and that is what he chose. That you can really start doing something, as Grothendieck posed it, just drawing on so abstract surfaces. And the title of this domain on mathematics just meant that any child can draw pictures on the surfaces. But then a very important event happened, and the Belyi theorem that is going to be formulated today reached him. In fact, he did not stop all the contacts with the community, and Pierre Deligne continued telling him what is going on. Belyi theorem is was unfortunately a mathematician from the same Shafarevich Moscow School of Algebraic Geometry as I'm from, and the theorem came from, in fact, inverse Galois theory, that is from arithmetic geometry. And then Grothendieck understood that his fate was still to work in the traditional field in which he was famous for, algebraic and arithmetic geometry. So he has written some text that is not mathematical at all, but contains lots of great ideas. Then myself and my Voivodsky published some normal mathematical text where some ideas were extracted from Grothendieck's text, Esquisse program. And starting from then, there are some people working in this domain. I mean, here again, down-to-earth part of this domain. Now I'll start explaining what it means. Okay, so it is a bit more convenient to formulate statements in category terms, but to understand the essence of the theory, it is quite sufficient to think in set theoretical terms. So the adult definition of descent d'enfant is like that. We take a triple where the largest member is just a compact connected oriented surface. What is stressed here is that it is not just orientable, but it's important to choose one of two possible oriented. And then there is a small restriction of concerning the graph embedded in the surface. So the complement to it should be the disjoint union of open disks. And then the graphs, not to say much words, is defined in the same terms. Just x sub 1 is an abstract topological subset, such that the complement to some finite set to it is a union of real intervals, of course, called edges. So there is some, so the category of the sense is not just the category of two-dimensional cell complexes, because the morphisms in this category are more delicate, let me skip it, because informally we understand, as usually in category language, that we are considering the mappings that respect the essential structures. Since we work in topology, there are the admissible classes of admissible maps just well satisfy this condition. But in fact, as I said, only once we'll consider the set of classes of equivalent Dessins as category, just when we relate it to some other category looking very different. So we move further, and we start with introducing the category which belongs to a totally different world, completely algebraic geometry. So it happens over an arbitrary algebraic closed field, and we consider an arbitrary smooth irreducible complete curve over this field, and we think about rational functions on it as about mappings to the projective line that we are going to draw and suggest to imagine as a usual line. So a Belyi pair is a pair of a curve and a rational function on it with a very special property. It is critical value. I'll use as synonyms critical values or branch points that are contained just in this smallest number. Well, it is shorter to say that we consider rational functions with no more than 3 critical points, and then we can put them to this distinguished triple just by a fractional linear transformation. It's important to see this object, and what is drawn here is something like ramified covering of a projective line, and over complex numbers it is just a Riemann sphere, and this covering has arbitrary branching over 0, 1, and infinity, and no other branching. I was trying to draw it here, that meaning that in over all the other points, like the red unnamed point here, it is unbranched. So these objects constitute an obvious category. Here, I don't know why I used complex numbers, just because they are traditional. But as you see, the definition is purely algebraic and is quite interesting over any field. Now we just to support my point of view that this is interesting, the object is interesting, I give just 2 examples, though I could give much more. So as soon as we consider generalized Fermat curves, that means affine curves defined by this classical equation, then, well, except from some, well, cases when the characteristic of K divides M or N, you can check very easily that the Fermat curves carry the Belyi functions like this. And there is another quite classical domain in algebraic geometry, the curves with many automorphisms. These many can be defined as a precise definition. However, if we have really many of them on some famous curve, like Klein quartic, and other well-studied curves. Just the factorization over the whole group of automorphisms is often, in fact, if we have really many automorphisms, then sorry for my mistake, it is always Belyi function. So this is quite a natural domain of algebraic geometry. Well, now we relate what we can do in algebraic geometry and what we can see or draw. Now I introduce some rather special object. I call the Belyi sphere just a usual Riemann sphere, the projective line over complex numbers, but colored in a special way. So here is the real line. Now I suggest these colors just to for being easily remembered, because, well, in our civilization, so what is drawn here in colors is a real projective line together with the infinity there, and well, red means hot, close to plus infinity, blue means cold, and green is inside. Or in alphabetic order, we have blue here, then green here, then red here. So we color it once forever. And then it is rather easy, though sometimes needs some time, to understand that whenever we have a Belyi function understood as a ramified covering of a usual sphere that we color in this way, then such an object, a Belyi function on an algebraic curve, or if you like, on a Riemann surface, defines the special coloring of the Riemann surface that is drawn here, and we call it the color triangulations. Triangulation meaning that it is really a triangulation, and of course the points colored black go to the lower, go by the mapping realized by beta, go to the lower hemisphere, and the white ones go to the upper hemisphere, and the mapping is unramified away from the vertices of the triangulation, and the combinatorics of such a mapping is such that any triangle contains the vertices of all the three colors and the edges of all the three colors, with the obvious rule from elementary geometry perhaps that any side of a triangle is colored in the same way as the opposite vertex to it. So it is not a too difficult theorem saying that we can study Belyi functions over complex numbers just studying these color triangulations. These classes of isomorphisms are in one-to-one correspondence, and we are going to say that this color triangulation paints such an algebraic, an object belonging to algebraic geometry as a Belyi pair. Okay, unfortunately, we'll have to spend some time considering the non-colored version of the theory as well. The one with which I started. When I explained what a descendant fung is, there was no coloring, as you see. There is a small technical detail that we'll overcome soon. So the trick is as follows. Among the Belyi pairs, we distinguish the so-called clean ones. That means that the branching over 0 and infinity is still arbitrary. There are no other branching, but over 1, it is exactly 2 to 1. Here is the boring algebra geometric definition with the standard concepts like a local ring, the stalk of the structural sheaf of the picture. So for those who are fluent in the abstract algebraic geometry language, it is quite a clear things. And if there are people from other domain of mathematics like logics, I think that this picture is clear enough is in itself. So as for the clean pairs, perhaps I have it on, no, I have had to omit something, and I just tell you that the original concept of descent d'enfant just associates to a clean pair the same Riemann surface with the pre-image of the segment 0, 1. Now, please believe me, it is easy to check it, well, just drawing some simple, really childish pictures to see what I see. Now, we have a square of, in fact, category equivalences. And on the left side, we have a pair of purely algebraic geometry concepts. So this is a cleaning functor that, well, was it written down? I hope, yes. Here is a simple procedure of cleaning. Some people can recognize this famous function. So this is the cleaning here. Here is the painting that we have discussed. Here is the drawing that is discussed here and that I described in words before. And sorry for this nasty abbreviation that turns the colored descent d'enfant into a black and white one. Just in this word, we take blue and red vertices to define just vertices and connect them with the green edges. In this way, we get just a graph on surfaces or a descent that was introduced in the beginning of the talk. Now, there is a technical fact that I'm not going to get into details of, but informally, it just means that working with Belyi pairs, unlike, well, maybe working with other objects in arithmetic geometry, we can really switch on our geometric imagination, maybe in the same way as we do elementary geometry. Elementary geometry is both rigorous mathematics and geometric understanding of it, and the theory we are speaking about has the same feature, but starting from now, well, maybe even here I say informally that as soon as we think about all the Belyi pairs or all the curves. In other terms, we are led to the moduli spaces, the main subject of my today's talk. So this is like that, but before that we need another equivalence that relates here to algebra geometric theories. Here is Q bar, the field of algebraic numbers, and Belyi theorem relates all these combinatorics not just with transcendental objects like here over complex numbers, but to other objects with the same definition, but defined over the field of algebraic numbers. What is really important here that our graphical domains were definable in finite pieces of information, and the arithmetic-geometric objects like this were the same things. Any, algebraic number can be defined as a root of polynomial with integer coefficients. This down-to-earth part of the theory that I mentioned in the beginning of the talk just relates two classes of objects defined in finite pieces of amounts of information, but belonging to two different worlds. So these two categories are equivalent. Now, an easy half, it is easy to understand that as soon as we have a Belyi pair over complex numbers, then in fact its ramification can be expressed in algebraic terms using only integers, and therefore it is after some thinking about this equivalence becomes clear, though there are several publications where the authors describe the details of this theorem using some deep results from abstract algebraic geometry. What is really difficult and fascinating, and what Grothendieck wrote about in a very poetic form, that as you see, all the curves over algebraic numbers are in the game. This moves us immediately to moduli spaces, because we can think about the curves over algebraic numbers as points, in fact, as everywhere dense subset of moduli spaces over complex numbers. Though I have not yet written it, we'll see it in the further slides. Now, here is some technical details that we perhaps skip now. So now I just fix some notations. They are more or less standard, but notation concerning moduli spaces, but sometimes used differently. Omitting the second argument just means that we have now specified points like here. And what is important to note, that in modern text, unlike the classical texts of the middle of the 50s and 60s, 60s of 20th century, the marked point are supposed to be ordered. That is perhaps not written here. And The moduli space, as perhaps most of you know, are non-compact and singular. They are quasi-projective varieties of well, very known dimension like this, but they have singularities corresponding to the curves having automorphisms. And then people use these level structures, these pairs of a curve and a set of points on it, and some other object. This object just belongs to the finite set of the possible isomorphisms of the homology group of a curve with finite coefficients with the abstract group isomorphic to this group. So what is important is the choice by this iota, and fixing iota makes this set of equivalence classes of curves and some points of them and additional structure makes this covering of the moduli spaces smooth. Well, usually means under some a small number of exceptions. So here is the technical point that will be useful just to work with, to apply the techniques we are discussing. So in my abstract, I promised two kind of relations between descendant functions and moduli space. Here's the first one, quite striking. Well, I should say that the moduli spaces are very delicate objects with complicated geometry and topology, and for example, the complete cohomology rings of them are still not calculated. However, there exists a cell decomposition, not exactly of the moduli space, but we should take a product of it with the real positive octant. And then to give precise results, we have to consider these classes of equivalence of sets of descendant function. However, without further restrictions, these sets are infinite. For example, you can draw any descendant function on a surface of genus G with n cells and add, well, tails or beads to it. So we impose some restriction. The most traditional is to forbid tails and beads. And then these sets become finite. And here I give a simple example of what can we draw on the torus. 1, 1 here means the first one is genus 1. The second one means that we are considering descends with just one face. The complement, the graphs are just cells. And here are just two possibilities. Either it is the hexagon with the opposite sides pasted or the square with it. So now we use the obvious notation E of D is just the finite set of edges of corresponding descent. And to introduce this cell decomposition we are speaking about, we have to consider a further structure, a very simple one. Just assign some positive real numbers to all the edges, and of course call them just lengths of edges. And here is the set of metrized ribbon graph with the same indexes, genus G and N faces. So what is drawn here is, sorry for forgetting the closing brace here. Just lambda has the interpretation I have just mentioned. Now there is a mapping, I call it Kontsevich mapping, formulated in the end of 19th, that just uses this continuous structure. And sorry, I had to use the tiny font to explain this this mapping. But in fact, it is an easy one because, well, I was lazy enough to draw the picture, and I'm restricted by the time. But we cover the initial, fixing this length, we cover the surface with semi-strips, where the directed edge has a width defined by lambda. And then we put the only complex structure to these semi-strips. And the combinatorics tells us how to glue them between, how to glue these abstract semi-strips in order to get not just a topological surface, but a surface with the complex structure. Though initially it seems that the transcendent constructor is purely real. We see nothing of a complex structure, just in the in the objects like metrized ribbon graphs. However, there is a fantastic fundamental theorem which was born long ago in the middle of the 20th century and belongs to people like Streber, who were not interested in modular spaces at all, and they considered no examples because they were purely transcendent people. However, omitting the detail, it means that this construction defines a homeomorphism. Therefore, the modular space, well, times some real octant, becomes what was promised. It becomes covered by the open cells, marked, labeled by descendant downfall. So this is the corollary I mean. Now maybe we skip this part because, well, it was extremely famous in the end of previous century and the beginning of this ones. There were 3 or 4 Fields prizes related to this construction, and just considering the volumes of the pieces we have discussed, we get to, well, some domains of modern mathematics or mathematical or theoretical physics with the generating functions for these volumes that satisfy the famous differential equations of mathematical physics and so on. So this is a really involved piece of mathematics. What I didn't mention here, that it has a definite well, homological appearance. The initial goal was not to calculate the whole homology of modular space. As I said, they are still not calculated completely, but there is an algebra of some special so-called topological cycles in the moduli space that the intersection of which is covered in terms of these theories. So what I really like to mention seems very fundamental to me and getting not enough attention. I think these three mathematicians are not very well known, but I hope we believe that this equivalence is fundamental, but there is something even more fundamental. It is the case when all the lengths of the edges are commensurable. Since they are defined up to common rescaling, we can consider them as natural numbers and return to the initial descendant functions, measuring them just with additional beads on the edges. Sorry if I speak too quickly, but I want to get to the end of the material. Anyhow, the part of this isomorphism is related both to some very simple and fundamental combinatorics. The two here means that now we allow the vertices of valency 2. And then on the right-hand side, we have some maybe children combinatorics, the things that are very easy to produce. And on the left-hand side, we get all the curves over all the algebraic numbers. So this is a strict set theoretical equality that, well, sorry for repeating, I think did not deserve enough attention now. And I'm happy to extend a bit the part of community who just knows that such equivalences exist. So this was the first connection that I have promised. The applications up to now are rather poor, though not empty. As soon as we have cell decomposition of something, it is enough to calculate homology in quite a combinatorial way, just taking the boundaries of the cells that naively, when we think the cells in descendant form terms, taking the boundary operator just means squeezes them to, or tending the lengths of the edges to 0. But it is the really naive point of view just because of automorphisms. This is the moduli spaces are really the orbifolds with some singularities. That's why we use here the level structure. Now, what is it about? I'm just quoting the only application I know of this construction I know. It means that once the curves of genus 2 just with one marking and with the level structure of order 3. But just to calculate this object several years ago, we needed the supercomputers, and well, my co-authors are young people, young physicists that were on very good terms with supercomputers, and according to their estimate, these direct methods cannot be extended, or they need supercomputers. Maybe we'll return to it when the quantum computers appears, but for the time being, it is perhaps on the boundary of the computer possibilities, just to calculate these homologies and to get the Betti numbers that are consistent with the known ones calculated by traditional techniques. Now, with all the question marks, I list some obvious directions of possible applications. So the other homology, as I said, needs either more advanced and wise methods than the direct methods than just using the cell decompositions to calculate homology. Well, but as we saw in the, as I mentioned before, some piece of homology is known, and it can be checked using these techniques. I think it is quite interesting. And as for other cohomology theories, there are lots of them, including the purely algebraic definitions. As you see, our construction is a terribly transcendental one. But there are algebraic definitions of all the cohomologies of algebraic varieties, including the moduli space. So hopefully this transcendent picture can be related to something algebraic. I think, as far as I understand, now to date, this question is completely open. Well, and here I mean that perhaps I've listed just the most obvious directions of applications. Now there is another relation that was promised in the abstract of this talk, maybe more obvious than the previous one. So now I use Hurwitz space, understanding that it is the pair of a curve and a rational function on it, and we define its filtration by the numbers of critical points. So we include in certain strata such pairs that, the branch points, the cardinalities of branch points are bounded by certain b's. So we have just these parameters are very well known in algebraic, for algebraic geometries. So this is what the critical filtration is. Now it is related to what we have discussed before in an obvious way, because the last stratum consists of Belyi pairs, the curve, and of the pairs, a curve and a function on it with exactly 3 critical values. That means just the Belyi pairs we have discussed before. Here is the, again, the name of the corresponding category. So we know very well for any fixed pair of integers d and g, we get some finite set labeled combinatorially by Dessins function. And what I stress as an interesting object is the penultimate one, that is the set of pairs, a curve and a function on it with no more than 4 critical values, and it is some complex graph that connects the Belyi pairs. I think that the structure of this graph is interesting and basically unknown up to now. Okay, but well, the Hurwitz spaces are perhaps do not have any well, standard definitions in the literature, and I find it much more handy to project the whole structure to moduli space that I express here in underlining. So we get this kind of objects. And I box it just because it seems the most fundamental to me, and because there are some people in the audience, among whom I know Krista, who work with different subsets of moduli spaces. So here is another one, a critical filtration. Let me repeat what it is. So fixing D, first we fix the genus, then we fix D, the degree of a rational function, and we consider the curves that can carry a function of degree D with the bounded critical value. And just again, let me simply repeat it. Again, the smallest term of this filtration is just the set of Belyi pairs, and we know that if we take all the degrees, what we get is just the modular spaces of all the curves over Q bar. And well, the central object of my current work is describing, as I said in the summary, describing the combinatorics of these pieces and arithmetic, what fields are they are defined over, and geometry, for example, how do they intersect, what are the multiplicities. And finally, the last slide means just an example with a twofold goal. First, I want to explain the origin of appearing of freed nets appearing. It was the result of our collective calculating Belyi pairs of a small number of edges. Now here we see the complete, maybe if you are not too used to such pictures, is not so easy to see the toric descendant function drawn by these pictures. As usually we identify the opposite sides of all these squares. And then we have some simple pictures with no more than 4 edges. And this is the complete list of such descents with just one face. I'm discussing just the relation between arithmetic or arithmetic geometry and combinatorics. And this example was important to understand that the objects that are simple from one point of view these combinatorial objects are really one of the simplest. If we take small number of edges, the calculations becomes trivial. And as you see, the corresponding arithmetic is terrible. And J invariants just depend on nothing arbitrary. So we can just, I can just write here for this cubic Galois orbit, the J invariants are the roots of some terrible cubic equation. Well, there is some obvious meaning here. Perhaps somebody will understand me that it means that the corresponding elliptic curves have terribly bad reduction, modulo 2, 5, and 7. It would be nice to be able to see these primes of bad reduction combinatorially. Here, what we, well, 5 is obvious everywhere, 7 can be composed out of valencies, 5 plus 2 and 6 plus 1 here. And we have some partial explanation of it, but not complete, the complete one. So this terrible calculation led me to, they all lie on the edge of freed net. So they can be in some continuous way deformed to each other. And I'm just mentioning one exciting edge of the freed net that I am advertising. And just my time is over. Thank you for your attention.
Okay. We thank you very much for your interesting talk. Do you have any questions or comments? You simply can speak and unmute the microphone and ask the question or to have the comments.
I hear everybody.
So do you have some comments?
Yes, I would like to ask a question.
Yes, please.
In regards to the filtration of the Hurwitz space, there is, I guess, an assumption on the degree D that you consider.
Probably. Should I return to the corresponding slide, perhaps? So here,
yes. So is there an assumption about the degree D, like being greater or equal than some number, like?
Yes, the assumption is, sorry for omitting it, the assumption to make this
yes, I understand.
This filtration complete, we should, well, can I write? It is complicated, may I just pronounce it. The assumption is that D is at least 2J plus 1.
Yes, I'm also curious about the filtration. What you have farthest on the right, on the Belyi pairs.
Yes.
Are they just isolated points in the moduli space?
Sure they are.
Is there an estimate how many exactly?
Oh, this is a great question, because the answer is in terms of the number of descendant functions, just by the main theorem we have discussed. The answer is by the number of descendant functions with a certain combinatorial characteristics. They are in one-to-one correspondence with certain descendant functions. So instead of, well, honest answer to your question, I say that the number of these points equals the number, say, of descends with a certain of certain genus with a certain number of, say, edges. And this counting descents is a very active domain of modern mathematics and physics.
Yes, and I'm curious also, one more question in this regard. If we think of those curves that admit...
If we think, sorry, what?
If we consider such a curve that admits Belyi pair, like, does it have some special properties, like geometrically?
Perhaps I should answer no, because according to the hard, difficult part of Belyi's theorem, it can be an arbitrary curve over Q bar. So an arbitrary curve, perhaps by something like definition, an arbitrary curve over any field has no special property. But of course, some properties, like say being hyperelliptic or so, can be expressed in terms of the corresponding Dessins.
Yes, thank you.
Do you have other questions or comments? Okay, if no, let's thank the speaker once again for the nice talk. Okay, we should. And now is the time for free chats.
Okay.
Okay, so shall I stop recording?
Sure, yeah.